So good morning to all. So today we are discussing in the second module of statistical physics. So here the first topic we will be discussing about microcanonical ensemble. Okay. In the last module we have discussed about elements of ensemble theory. In that session we have said that an ensemble is a collection of different microstate within a macrostate. Okay, and also we said that it is a Mendel copies of different microstates. Okay, and in also we have seen that there are three type of ensembles are there. One is microcanonical ensemble, the other one is canonical ensemble, and the third one is grand canonical ensemble. Okay, so these are the three ensembles we have identified in the last module, and today we will be addressing micro canonical ensemble. Okay, so we know that whenever we represent a microstate, in our earlier discussion we have said that in a microstate the number of particles, the volume and the energy will be constant in a microstate. Okay, such a different microstate, okay, within a macro state we used to call it a micro canonical ensemble. So whenever you are dealing with a micro canonical ensemble, the number of particle and the volume and energy will be constant at a different micro state. Okay, so that's what we used to call as microstate. In a region of microstate, this number, volume and energy will be constant. But also we identified that there is some leakage will be there. Okay, so there is a leakage of energy we have noticed, and we also find that it is always better to represent energy in a particular interval. Okay, so not to consider energy as a constant energy term, but energy can be represented in a particular particular interval. Okay, so by that idea we do represent energy like this fashion, that is E minus delta by 2 and E plus delta by 2, where the difference is basically the delta. So that's how we will be getting the corresponding change in with respect to two energy levels. And by considering that we also made a phase trajectory, hope you remember that. Okay, so in that phase trajectory, sorry, so in that phase trajectory, where we phase trajectory we actually plot P with respect to Q. Okay, that is the momentum with respect to the coordinate representation we do represent. So this is we call it phase space, right? So in that case we'll have a hyper shell structure. Okay, we have a hyper shell structure like this. Okay, so these are two circles and we represented with the center. You assume that center is at the origin, and we said that this is having the energy that is E plus delta by 2, and this one is E minus delta by 2. Okay, there is a separation between that is delta by 2. Okay, and in the discussion we also said that whenever you consider the representative point is a phase space point. Phase points or phase space point we used to call as representative points. Okay, also we say that representative points are microstates. Okay, so the representative points can be found in this region where E minus delta by 2 to E plus delta by 2, this interval region where we are finding different microstates. Okay, so that is already we know that. So also when you consider the total energy, so when you consider the total energy in the region, that means this interval region we will be identifying different microstates. Okay, so the total energy when you represent, we do represent it is in the Hamiltonian form, right? That is Hamiltonian total energy HQP. So which will be having the value that is between E minus delta by 2 less than or equal to HQP. Okay, that is Hamiltonian, which is less than or equal to what? E plus delta by 2. So the total energy will be lying in between E minus delta by 2 and E plus delta by 2. That means you can find the Hamiltonian that is in between in this region. Okay, and as I said, this value of the representative points you can identify in this particular energy interval only. So in that period, the in this case, when you consider the density rho qpt, so it is actually the density, right? Okay. So the density is equal to rho qpt. We all already discussed about density function and all. So rho qpt will be the density of this space, this region, this shaded region, this dotted region will having the density corresponding to that. And in this region, we said that for a microcanonical ensemble, the density will be what? It will be a constant value. So the density will be constant because the energy, number of particle, volume, energy and all things are constant. So it will be the density also will be constant in that representation. And we know that what is density means. So it is actually giving the idea of the number of representative points, okay, or number of microstate, number of representative points divided by volume. So that is we call as the density correspond to this one. Okay. Now in general, whenever you represent a microcanonical ensemble, okay, the microcanonical ensemble case, we have a specific representation. So for microcanonical ensemble, it is a collection of ensemble which actually following a condition, which is actually following a condition of the density, that is rho qpt is equal to a constant. When it will be a constant? It will be a constant when if E minus delta by 2 less than or equal to Hamiltonian QP less than or equal to E plus delta by 2. So whenever you have a energy Hamiltonian, total energy Hamiltonian, that is HQP in between E minus delta by 2 and E plus delta by 2, and your density will be constant at that situation. Okay, and also we can say that it will be 0 otherwise. Okay, otherwise the density will be 0 in the other case. And also from the above representation we'll get an idea that we said that rho qpt, rho qpt equal to a constant. Okay, it's a constant that is equal to what? Number of representative points, divided by the unit volume. So that is unit volume corresponding to that. And in this representation, since rho qpt is a constant, we'll get an idea that number of representative points in the region, the dotted region, will be proportional to what? Proportional to volume, because here rho qpt is a constant. So when you take volume on the left hand side, so you can actually say that number of representative points is proportional to what? It is proportional to volume. Okay, so we'll get an idea like that. Now let me just go back to the figure again. So, and I said that in this figure, when you represent this figure, so the volume in this region, the volume in this shaded or dotted region is, we can represent as omega. So omega is the volume of the phase space region. Okay, so it is a phase space region where omega is the volume of that. So which is actually what? So this is the volume of this entire space region. Okay, and also I have represented different microstates, right? So gamma is actually representing the number of microstate or number of representative points. Okay, and omega is the volume of phase space. And now if I consider the volume of a single microstate, okay, the volume of a single microstate, then that will be omega 0. Omega 0 is a volume of a single representative point or a microstate. Okay, so we will be only considering this phase space region where we have given a different dot, the dot corresponding to different number of representative points. Okay, these representative points you can either call it as microstate. Okay, so now I'll say that omega is the volume of, okay, volume of the phase space region I have drawn above, phase space region. So this I can identify, that is omega equal to integral d omega dash is equal to, it is actually taking dq raised to 3n and then dp raised to 3n. So it is actually d omega, you can take the integration corresponding to that, then you will be actually taking the volume of that phase space region where we will be having the number of representative points. That is means you will be only considering in that particular interval region only. Okay, so you got the omega corresponding to that, and I said that the omega where gamma is basically representing the number of representative points, number of representative points, or you can either say that microstates. Okay, number of microstates you can represent in that fashion. Okay, so now I also said a terminology, that is omega 0. Omega 0 is a volume of a single microstate or a representative point. Okay, see, volume of a single microstate, which is also called as fundamental volume. Okay, which is also called as fundamental volume. Okay, now from this relation, omega is the volume of the phase space region, gamma is the number of representative points or microstate, and omega 0 the volume of a single microstate or a fundamental, or either we can call it as a fundamental volume. Okay, now if I want to find the number of representative points, that is gamma, so that is gamma equal to what? Gamma will be total volume of the phase space region with divided by a single volume of a single microstate. So from that I can identify the value of gamma representation. Okay, so gamma equal to omega by omega 0, where omega 0 is the volume of a single microstate, omega is the volume of the space region, the entire space region, that is we are representing there. Okay, now let me share you something more, that is I got the value of gamma. Gamma is basically what we said, that gamma is basically the microstate at a particular energy interval. Okay, it is a microstate at a particular energy interval, because we have executed different calculation based on that earlier. Okay, particular energy interval, like that fashion also we can say. Okay, and when you represent by Boltzmann relation, okay, by Boltzmann relation we have a relation of entropy. So that is entropy S is equal to what? S is equal to kb ln gamma. Hope you remember this equation. Hope you remember this equation, that is S is equal to k ln gamma. Okay, so once you got the entropy representation, what is gamma now? Gamma is omega by omega 0, that is kb ln omega by omega 0. Okay, so this is your entropy equation for a microcanonical ensemble case. Okay, so once you get an entropy corresponding to a system, you know that you can identify the energy associated with that, you can identify the pressure associated with that, you can find the temperature associated with that, because we have done those things in the last classes, no, last module we have done that. So while you got the entropy value, you can actually derive pressure, temperature, energy, like the different thermodynamic parameters you can actually derive from that. Okay, I'm not going to derive further, but you can do that, and you can do that by yourself. Okay, so that is not our point of discussion. So what I just want to share is that will be the entropy for a microcanonical ensemble will be kb ln omega by omega 0, where omega is the volume of the phase space region, omega 0 is the fundamental volume corresponding to that. Now what we having either is that, so it's about entropy of a microcanonical ensemble. So that relation is very important, because further when we are discussing that. And also we have to say that when you consider the ensemble average of any function, that is, this function can be either a time, this can be any number, it can be a volume. So it's ensemble average of any function, we can say that it is basically, what is this representing? The ensemble average of a function, that is f. Right. Okay, now if I consider a stationary ensemble, okay, so I consider that a stationary ensemble case. In that case, we know that the time is not varying in that case, so I can take the time average. So I can do represent the above equation as a time average of what? Time average of a ensemble average. Okay, so which is basically giving the idea of a what is the resultant value, ensemble average of t. Okay, sorry, f, corresponding to that ensemble average of f. And or rather we can represent, because time average and ensemble average are independent quantity here, so in that case we can either do represent this equation as the ensemble average of, it is the ensemble average of time average of a function f. So how do I represent this one? Because already we said that when we have a function f of x y. Okay, now if you take dou square f by dou xy, okay, dou square f dou x dou y, you can either write this function like this, that is dou square f dou y dou x, both are equal. Okay, so in similar fashion you can actually take the time average of ensemble average of t and ensemble average of time average of t, you in order to find the value of this function f for a case of any ensemble. And also when we say that when you consider any ensemble, okay, when you consider any ensemble for a longer time duration, so longer time duration means the process will be almost saturated. There you don't want to take the ensemble average. After a time period, it is almost whatever your the data or the whatever the process actually giving you a average of that all contribution towards that. Okay, so if you are evaluating any process after a long time, so the process will be almost saturated, almost it is giving a equal contribution from all sides. So you can say that in that case you can also find the long time average of f, long time average of f, so that you don't want to take the ensemble average and the time average separately, so you can directly take the long time average of the function f, which is actually giving the idea of the average value of that particular function. Okay, and now when you consider any function, that is, for example, if you say that the experimentally if you calculate the ensemble average of function f, in that case normally the experimental value that is you're gonna get, it will be the expected. So average f means it is the f expected value that is you gonna get it in the case. Okay, so what I was trying to say is that The ensemble average of any physical quantity. The ensemble average of any physical quantity, okay, any physical quantity f is identical with the value of the expected average, okay, expected to obtain by making any an appropriate measurement, okay, measurement on the given system. Okay, so the ensemble average of any physical quantity f is identical with the value of expected to obtain by making any appropriate measurement on the given system. That is, just to say that, so the value will be the expected average of any ensemble will be, so the value that is experimentally you are expecting on that case. Okay, it is just simply I just represented, because on an experimental observation, when you consider ensemble average, it will be the average contribution of all different values. Like you can when you consider an ensemble where we have a number of particles, volume, energy, representation, everything is there now. So after a long time, so this all will be getting saturated, all will be contributing in an average fashion. So whenever you take the ensemble of that, so you can actually get that after a long time, so you'll be getting the average value of all contribution. So it is as expected, so the average value will be getting the same by the experimental expectation side. Okay, so that's about a microcanonical ensemble. Basically I want to share, so what we have mainly we addressed is that microcanonical ensemble case. So microcanonical ensemble case, we have to say that the first one is that rho qpt, that is the density. Okay, the density is a constant in the allowed region. Allowed region means that is a in that particular phase space region or that particular interval. Okay, so that is the first part we identified, the rho qpt. Also we have given a condition where rho qpt will be constant on E minus delta by 2 less than or equal to hqp less than or equal to E plus delta by 2. In that particular condition, the density will be constant in that case. That's the first thing we identified for a microcanonical ensemble. And also we said that for this case, the NVE, that is the energy, number of particles, volume will be constant for a microcanonical ensemble. For a microcanonical ensemble, number of particle, volume, energy will be constant. Okay, so it will be different for grand canonical ensemble, it will be different for canonical ensemble case. So NVE is the values will be the constant in that case. And the third one, in this case, for a microcanonical ensemble, it won't share any energy, number of particles, volume to the neighborhood systems. That means it is an isolated system. So microcanonical ensemble system is a isolated system where it won't share the number of particle, volume and energy representations, energy value to the neighboring, okay, to the neighboring systems. So microcanonical ensemble is a density is a constant in the allowed region. And second one, the microcanonical ensemble is defined by where the number of particle, volume, energy will be constant for a microcanonical ensemble. And the third one, it will be isolated system, that is it won't share the energy, number of particle, volume to the nearby systems. Okay, so that's about microcanonical ensemble. On That's all we have to discuss for today, and one on the next class we will be discussing about two systems, that is about one is classical ideal gas case. Okay, classical ideal gas, and we'll also discuss about harmonic oscillator. Okay, in these two cases, how do we utilize the concept of microcanonical ensemble? Okay, so that will be our discussion for the next class, classical ideal gas and harmonic oscillator in terms of microcanonical ensemble representation. How do we represent that? Okay, so that's all for today. You just be understand about what is ensemble is, what is microcanonical ensemble, and we'll also in detail we'll discuss about canonical and grand canonical ensemble in the following classes. But you have to have a thorough understanding of what is microcanonical ensemble is, that in order to address next two problem based on classical ideal gas and harmonic oscillator. Okay, so thank you for listening.